I think you have some discussion for us as well, and we'll have a Q&A section afterwards too. I know you all have prepared some questions for him. But thank you for being here today. I'll let you introduce yourself.
No, thanks for inviting me. So I'm Ali Nasseri. I am a physicist and an engineer. So what I do right now, I work at the University of British Columbia at a group called Programming Languages for Artificial Intelligence, which is not probably the best name for a group, but basically we work on machine learning tools that impact your life daily. For example, when you go and watch something on YouTube, that algorithm that YouTube uses, the basic principles behind that are things that we study. Before that, I mean, I was basically a physicist. I was studying magnetic materials, so I might talk a little bit about that a little bit later today. And as an engineer, I was an aerospace engineer, so I worked with unmanned aerial systems, or drones, which probably most of you are familiar with. I worked on space debris is another topic, and space safety. Okay, so what I did is I put something together to ask you a few questions for the next 10 minutes, and then I'll let you ask me questions. How's that? Works?
That sounds fantastic. Thank you.
Let's see if I can share the right window. You should right now see a blank page. That's the easiest way to start this. So I guess I've been told that you've been studying waves. And now my first question is, what are the main characteristics of a wave? Or properties of a wave, or how do you define a wave? Those are three different ways to ask the same question. Okay, Joseph?
Amplitude.
That's one of them?
Wavelength.
Uh-huh.
Frequency.
Yeah, so amplitude, wavelength, frequency. You really need, I guess, two of them, because if you know wavelength, you can get the frequency if you know where the wave is going. So amplitude and frequency or wavelength or the period of the wave, one of those three would work, basically, would help you define a wave. There is one thing that is not shown here is if I compare two waves, they might be in phase or out of phase. Have you studied that as well? So basically, I could have a wave that's a little bit forward this wave. So it might, like its peak instead of being here, might be here. So it might go like this. So the two waves compared to each other, we call them they're out of phase because they're not exactly, they don't exactly match each other when you move, when compared to each other. In phase would be if they match each other, basically. If you want to put it this simple way. So those are kind of the ways you can define a wave. Ways to define a wave. That's a lot of words. And you've probably studied all of these different types of wave frequencies that are available, and you've probably seen something like this, which tells you kind of what they're used for. But I have my next question, which is, let's say I have a wave, and I want to use it to communicate. Then how can I put data in the wave? Based on the characteristics that you know already of the wave. Any ideas? Asher?
Frequency modulation.
Okay, tell me more. That's one of them.
So let me see if I remember this. So amplitude of the wave would stay the same, but the frequency would change, or maybe let's switch, or the amplitude. I'm forgetting. I'm sorry.
Or both. Yeah. So you could have the amplitude of the wave changing, and then you could say the higher amplitude is your 1 if you're doing digital information transfer, and the lower bit is a 0, and then you can have 1 0 0 1 1, and something on the other side would understand what 10011 is, depending on what you're communicating, right? And that's amplitude modulation, or AM, which your radios have, AM and FM, right? And FM is if you modulate the frequency, meaning that the one, let's say, higher frequency or lower frequency is 0 and the other frequency is 1, and then you switch between the two to code 0 and 1. What I talked to you about, which was phase, that's also something that you can use to basically do modulation, which is called phase modulation. But I put this image here not because of the phase modulation, but to tell you how it actually works, which is you have a carrier wave and you have some sort of wave that interacts with it to create the message. And on the other side, the receiver end has to kind of subtract this carrier wave from this to get the message, if you're doing an analog communication. Okay. So you have something that encodes that data and you have something that decodes that data. That's cool. What I've used this for, other than, okay, I have a remote control to control a device, which is really cool. But there, I don't need to really know how this works. It works, right? The only thing I need to know is that if you have a controller, usually they have settings for different frequencies, and you just have to make sure that it matches, you match the two sides for it to work. But what I've used waves more interestingly in practice is this property of them, that the different sizes of different, I guess, frequencies, wavelengths, whatever, can let you interact with objects of different sizes. So if I want to see the nucleus of an atom, I can't use light to do that, but I can use some other form of wave to do that. And in our case, we had something like this. It's called a Kerr microscope. Kerr is an effect for light. Basically, if you have magnetic materials, light is an electromagnetic field. So the light would interact with the magnetic field, and some of its properties would change. Remember the modulation part? So it would be modulated, and then we can use that to extract information. This is an experiment we did. So these are some wires. The length of them, if I remember correctly, they're 500 microns. That's 500 micrometers. So that's well, I mean, it's very, very small length. So that's 500 microns. And then judge how much the width is. We were studying nanomaterials, so materials that are 1,000 times thinner than your hair, where we put layers of different materials. So platinum, in this case, is the underlying layer. Then we put cobalt on it. Cobalt is magnetic, so we wanted to study cobalt. And then on top of it, you can put platinum. In this case, we put platinum. You can put an oxide. You can put different things. What happens is when you put these materials together, the interaction between the cobalt and the platinum would give us new effects that we don't see, and that was what we were trying to study. But to study this, it's a nanowire, so like the whole thing, it's this size, and in it there's like a lot of wires. What we wanted to see is, if you look here at the image, you see that there are areas with two colors. So the two colors are linked to two different areas of magnetic property. So you can think of it as here is pointing north, here is pointing south. Okay. What we were trying to study is how fast this part is moving. How fast is this going to grow? In a hard drive that you use on your computer, for example, or the information is coded this way. So the areas with different magnetic properties are close to each other, and we should be able to make them larger or smaller to code data. So that's kind of why we wanted to study this. So because these are very small, we need to rely on different effects to study them. So there are different ways you can do that. one of them is using electromagnetic waves. In our case, we actually use light in the form of ordinary light or lasers. As I said, like this Kerr effect, when the light hits the areas that are magnetic, it might slightly turn when it's coming back, and we can measure that turn and kind of link it with the magnetic properties of the material, and we would be able to see what's happening here. And then someone had to do these calculations, but we can measure how fast this spark, which we call the domain wall, we call each of these a domain, and this is called the domain wall, how fast it was moving. I didn't do this experiment. Kosari did it, and I was actually trying to replicate this using modeling, so using computational methods to kind of see if we can get the same effect, or if we don't. If we don't get the same effect, then it tells us that there's a physical effect in the material that we don't see, for example. So that's kind of how, as a physicist, we use light versus in an engineering setting. Now, last question. What happens if two people use the same frequency to communicate with each other in the same room? So let's say Jacob and Rowan are going to send a message in class, and they don't want their teacher to know this message. What happens if both of them are using the same frequency? Let's say they're trying to send a message to Amanda, and they both use the same frequency. That's a better example. Any ideas? No? Did you study anything about interference or waves interacting with each other? No? Okay. Let's go back to our wave.
Mr. Ali.
Yeah.
Saying, I mean, Joseph has his name, Mr. Holmes.
Well,
Yeah.
I was gonna say that, like, if Jacob and Rowan were to send it to Amanda, there's this thing called resonance where Amanda would pick up those two signals and no other signals. But I don't know much else.
Okay. So let's look at this wave. So if they're both using the same frequency, they both have the same carrier wave. So this part is the same, right? And they are putting two different messages in this wave, right? If Jacobs puts one message here, he gets this. But Rowan is also using the same wave. He puts a different message, or they put a different message here that is like that. You get a different form of wave. It's impossible to decode the message because you have two interactions with the same wave, right? That's kind of what happens. And that's a problem because, as you know, probably in your already classroom, there are a lot of different devices using electromagnetic waves. And that can kind of mean that your phone suddenly would make the Wi-Fi go turn kind of signal go off or on, etc. This actually happens. So if you buy something that is not standard, then it might kind of interfere with other devices that you have. So to stop that, there's a chart like this. A very beautiful chart that you cannot read. I was trying to kind of make it larger. You can't still read it. This is called a basically frequency allocation. So basically and this is done at country level. So every country has an authority that is in charge of allocating what frequency is used for what purpose. So I couldn't find a US Zoom version, but I could find one in Bangladesh. So I'm going to tell you what it is. So each of these areas are used for a different purpose. So they would say, you're going to use this area of frequency for communications for mobile devices, right? Now, if you are a mobile operator, if you're a cellular phone operator, you have to go and register with the government and get a piece of this. So it looks like this. So these are different operators in Bangladesh. I guess that's the only thing I could find. And each of them is given a piece of that big pie of communication frequencies or wavelengths that are there for mobile communication. So they have to use this area. If they start using a frequency that is higher, their license would be revoked. So they would have to cease operation. Same happens in space. So when we send objects to space, every operator, satellite operator, has to register the object and get a frequency allocated for that object. And this is, again, done at every country level, which makes it a little bit tricky because if, I mean, in space, the satellites don't care which country they are over. They just care to send their message. So if they're over the wrong country, this might become a problem. So for satellites, this is sometimes done through the International Telecommunications Union, which is an organization that is global. But for most other purposes, countries have these rules. And if you buy a device that is equipped with radio telecommunication, depending on the country you are, it usually has a certification on the back. It's like something like CE or an FTC or something like that, that tells you that they have been standardized to work in a region or a country to prevent any form of interference. That's what I had for today. I hope that was fun. But usually your questions are going to be more fun. So.
Great, thank you so much. That was incredibly informative. Yeah, we'll open it up to all of you all to have questions. You can type in the chat or raise your hand.
Okay, so when you were talking about that microscope from earlier, you mentioned how like you're using light and then you're changing the light into some other kind of wave. Okay, that's kind of cool.
Yeah, so it's not changing the light, but I guess I didn't put a image, but I'm going to cheat and show this. So basically what you do is you put the light on, so the light is always hitting the object at an angle, right? And if you remember from your simple light physics, if you have a surface that is very kind of clear and everything, you expect the light to reflect and reflect at the same angle, right? In our case, the light might reflect, but it might reflect at a slightly different angle. And the slight change is the Kerr effect. It's called the Kerr effect. And there's a formula for it to calculate kind of, depending on how much the magnetic materials what the magnetic materials properties are, how much the shift would be from ordinary reflection. Of course, you have to take into account that the surface of your material is not smooth, et cetera, which is why the microscope manufacturer gets the big bucks to give us a microscope. But the simple effect is that basically it's reflection is slightly affected by the magnetic material, and you can measure how much that effect is based on how much the reflection is affected.
Thank you.
Your questions don't, by the way, have to be restricted to waves and light. So.
Asher?
Cool. So say we have a light wave coming at an object, right? And it's a clear object. So like say it's a prism. But like the prism has like different sides. Is it going to be the same angle bouncing off on all the different directions? Or is it going to be different angles when the light hits it and bounces off and reflects?
With a prism, you would have refraction more than reflection if it's transparent, right? So We are talking about materials that are not transparent, materials that we're studying. So that's why it reflects. But if you have a transparent material, then you have refraction, which has its own different rules, depends on what material the prism is made of, what environment you're in. All of those things come into play. So, the speed of light is affected by the environment. Yeah, so it's a totally different deal there.
Got you.
Anybody else wants to ask a question?
Today, you will be learning about refraction in your async work today, actually. So be sure to check that out. Yeah, Asher, what's your next question?
Okay, so I heard you've worked with drones before. Have you ever like actually owned your own drone or like messed with or tampered with any of the equipment in a drone to like soup it up or anything?
Souping up. I can tell you a story about that. I think this is a fun story, so maybe I'll let me share this. So one of the, I guess let's start with like the type of work that I've done with drones, and then I'll show you the story of one drone. I used to kind of supervise a workshop where our students at university, they would build a drone. So the idea was these students were studying aerospace engineering, and as their fourth year, the idea was to do a project where they use all the skills that they learned throughout the program. So the best thing we found was, okay, so we asked them to design a small plane, but then also build it. So that's the story I'm going to show you of one of these, what steps it goes through. I think it's an interesting story because they came up with very unique ways of testing things. Because when you're testing something in a workshop that is like your own, is different from when you're testing it in industry where you have tools that are for testing, right? But going back to the industry thing, my focus was on destroying drones. If you remember a couple of years ago, I think it was 2018, December, Gatwick Airport in the UK had to close because drones were flying around it. And they had to close it for 3 years. It was Christmas time, so people were stuck. They couldn't do anything. And that's a challenge that now exists. So in most countries now, if you want to fly a drone, you have to register your drone. If it's larger than a specific size, you need to have a license, a pilot license, so you know the rules. And these all came into effect because of problems like this, where people would fly something near an airport or an unrestricted area. So one of the other things then you have to think about is, let's say I'm the operator of the airport. So what happens if someone does fly a drone? So I need ways to bring the drone down. There are means of bringing drones down. They just cost a lot. So they're like a couple of $1 million. There are nets, for example, that would kind of go and grab the drone. Or there are other means of shooting a drone down, I guess. But what we were studying actually was one of those means of shooting a drone down, but a very simple mean. Can you use a projectile, a gun, to shoot a drone effectively? This was a project with the DRDC, which is Defense Research and Development Canada, because they were just interested in other means of bringing a drone down that are simple, which can be used for public safety purposes. So one is like using a gun. You can do, we just talked about electromagnetic waves. You can hijack drone's basically communication wave. And if you do that, you could control them and then bring them down. Or you can interfere with the communication with the drone to basically prevent control messages to get to it, which would then mean it just falls down. So those are other ways that you could do. But now, going to the story of manipulating, I guess, a drone, which is not exactly that, but this is how they built the drone. So you can use different materials to build a flying vehicle, obviously. contrary to what you might think, yes, the ones that you buy at a shop are made of plastic, but the ones that we actually use, usually they're made of things like wood, foam, metals, obviously, but like they're very rugged usually. So our students had access to wood and foam to build these. So an airframe is made of different structural components. So the first thing they would do is come up with what those structural components look like, especially if you want to use wood to make it. So they had designed the pieces. These are the pieces, and we had a 3D printer, so they could print it out of wood. So this is the inside of the 3D printer. So not 3D printer, sorry, laser cutter. I mixed. So this is the inside of the laser cutter where we were cutting the wood out, and then you get these pieces. These are called spars. So these are the structural components that prevent bending. So if you have a wing, they go along the wing and they prevent the wing from bending too much. And then you have your ribs, which are these, like the ribs that the person has. They give form to the wing because you want your wing to have a specific form. Our students had this group. There were different groups. I think we had 6 groups that year. So this is just the story of one of them. They reinforced their spar with some carbon fiber. So those are the black things you see there. But we wanted to see if this actually works or not. So a simple test, very simple test. You just put a weight and they tried to see when it breaks in bending. They can increase the weight until it breaks. So broke, they got an idea, so they broke 3 of them, but that's fine because it's just a laser cutter, so it can just cut it. They have a design of it. So it gives them an idea of when it breaks and the strength that it has. That's when it was put together. Then there's a motor that goes on this. Now, this is where real life is different from, I guess, what you have on paper. We have motors that we would give them, and these motors have specifications, which says, okay, how fast they go, how much. We had computer programs that can calculate how much force, thrust you can get from them based on what propeller you put on them. So those are all nice. The only thing is, these motors had been used before. They had been used for 10 years at this point. So we actually didn't know if they would kind of do what they're supposed to do. So this group decided to test it using this very simple way to see how much it pushes on the scale. And that gives them a measure of the force that they can generate. They then decided that they don't want this to break, and we had to do some testing. You'll see the testing later. So they said, let's make it out of foam too. So it had to be the same weight, the same shape, but out of foam. We had a foam cutter, so that's our foam cutter. So they cut this out again, and then they made this foam model of it. We took the foam model and then we tested it. So this space is the Mars Dome at the University of Toronto, which the ground part is used for testing rovers that are kind of simulating Mars here. But it was underutilized, and then they never used the top bits of it. So we just went there and we put a zip line, and we put the aircraft on them, and then we would basically run it through different speeds to try to see how it behaves. When you're designing an aircraft, the important thing is for it to be stable when you're flying it, because if it's unstable, then you have to control it all the time, which is what we do for like fighter aircraft and things like that, because you want them to be maneuverable. But for something like this, which is just supposed to fly, you want it to be stable in flight. I'm going to test that. What this lets us do is to see what behavior it has. So a sample, I don't think I have a video, but one of the behaviors that it has is like going up and down like this, which is something then you have to control, which is tricky. So we don't want that. So we tested this. And then as part of their mission, they had to maximize a payload. And the payload was golf balls, ping pong balls, and I think tennis balls. Those were the 3 payloads. They had a different score for each. And at the start of the design process, they actually calculated how much of each they want to take, what's the score they're going to get. So at the end, they had to then verify that they would get the same score. So that's why they are putting kind of ping pong balls there. That's their cargo bay, I guess. Yeah, so then they put everything together slowly, they cover it, they make sure they have access to the payload because we had to swap in and out. You need to have access to all your electronics. The radio transmitter goes here too. That's just testing that it moves. Most of the time, it actually would not go straight. This was a good, I guess, case where it did go straight. Can I go to the next one? Yeah. This is its testing in flight, I guess. This was the first time we were doing this test, so it's not that stable. The next year we bought a better motor. Here the motor was basically a human on a bicycle. Things we, I guess, do. Yeah, but then it flew and it won. Won the first place among the student teams. And yeah. Oh, I didn't know that. And then they had to tell us kind of why it won and how it behaved compared to what they designed. But that's one story of a drone from conception to flight.
That was really cool to see a drone built from scratch. I've never seen that quite before.
Sorry, what's that?
I said it was very neat seeing a drone built from scratch. I've never seen that before, so it's nice. That's cool to see. What a fun project. I have some list of questions from students who aren't attending here today too. And one of them asked, what inspired you to become an aerospace engineer? I know that's what you studied, but I know you also made the transition to physicist. So what also inspired you to pursue that next?
Okay, sure. Let's see. I guess I was born in the 1980s. So it's very old. But I wanted to ask this question for everyone. Anybody knows what space station was up there when I was a kid? Hands up, anyone? You don't need to answer, but no one? No. Okay. So that's one of the things that made me interested in space, actually, was that first space station. So let's see. That's the space station. It's the Mir space station that was launched. Actually, it was, I think, launched the year I was born. And then it was in space until 2001, 2000. I remember this, which is the Mir space station returning to Earth and burning in the atmosphere. Because they were building another one, which is the one that is up there right now, the International Space Station. So that was one of the things that kind of made me interested a lot in space. I remember that I was like reading about like people on the Mir and then people on the International Space Station, which, in case you don't know, that's the International Space Station Lego pieces coming together. It didn't end up being like this exactly. It's much different now. But yeah, so then I was seeing people on this. So this was one of the, I guess, inspirations for me to go and study aerospace engineering. But there was another one. Anybody knows any space telescopes here? Okay, Joseph.
I believe there's the Hubble Space Telescope.
That's the most famous space telescope. And yeah, so that was another one, seeing these photos of space. And I remember clearly when Hubble turned 15, and I was more or less 17, I think. That was another thing that was cool. In reality, there are a lot more space telescopes. Hubble is the most famous because it looks deeper. It has an interesting story, and then it generates images that like you can look at, versus like the more scientific ones, which a lot of times they're not communicated to the public. So those were the two things that actually got me into thinking about aerospace engineering and getting into space-related stuff. And physics was, I guess, just by chance. I got a job in physics. That was interesting. One of the things I guess that I learned is as you go further in your kind of studies, there's no clear line that separates, let's say, a physicist from an engineer, from a computer scientist. Not in the sense that you don't. So basically, you can learn a lot of the same things that someone from a different field knows even later on. So you don't need to start in that field. And a lot of times, being from a different field brings unique perspectives that they might not have. So I work with computer scientists right now. I am not a computer scientist, but I used to develop a lot of computational models. So that's kind of what I know. They know more about like proper software development, which I don't know much about, and I'm not that interested in. But still, like when we do projects, I can contribute because of that different perspective that I have, which is the applied side of things. Yeah, but that's the story of aerospace and physics.
Great, thank you. It's interesting to hear too that physics and engineering can like overlap so much later on, because our course is actually taught physics and engineering in combination here at the school.
Yeah, I can actually add one more thing there, because when I was doing my master's, I was in the aerospace program. So like the drone thing that you saw, that was a course I taught when I was doing my master's. And I was in a group that was a combustion group. So we were studying how fuels burn, right? But the project that was given to me was modeling fuels. There's only a problem. I had never taken chemistry at university level. And this was like organic chemistry. So I had to understand all of these like chemicals that have carbon and hydrogen in them. So I still didn't take a course in chemistry. I continued doing my work, and I learned kind of things that I needed for the project myself. I took my chemistry course 3 years after. But still, like basic chemistry, I knew from high school. I was always good in chemistry. That was, I guess, the positive side. So I could understand what the chemistry is, and then I picked up what I needed as I went on, just to give you a little bit of an idea of what it was about. So anybody knows what an MRI machine is? Right? MRI machines they use magnetic resonance, so to image the body. What that means is basically they create a magnetic field around you. And by changing the magnetic field, different parts of your body would interact differently with that. And by measuring the different interactions, you can kind of get a picture, a map of the body. Now, this is not unique to the body. It's because your body is made of atoms and molecules. And this behavior is actually the behavior of atoms. So in chemistry, we have something called NMR, which is nuclear magnetic resonance. It's basically applying a magnetic field to an atom or a molecule, and then see how it behaves in response to that, and using that as a measure. So every molecule or every molecule would have a different signature when you apply a magnetic field to it. By applying a standard magnetic field, you can compare different I guess, different molecules to each other. And that was kind of what we were doing. We were trying to build, basically we had the jet fuel. Jet fuel is like similar, very much similar to the fuel you use in a car. It's just heavier, so the components are different, but it's similar in the sense that if you go 2 different days to the gas station and you get your gas and you do a test on it, a chemical test on it, it behaves the same way, but the detailed components that it's made of might be slightly different. And that's a problem when we want to study jet fuel in a lab, because we want to be able to replicate our experiments. So if we do an experiment today and tomorrow, we want to be able to compare them. But if the fuel chemistry changes, we can't do that. So to solve that problem, you use something called a surrogate fuel. So it's a chemical mixture, has the same properties as the fuel, but it's controlled structure. So you can make it in the lab and you can do all your experiments with it, and you know that it behaves the same as the fuel. So what I was doing is I had this NMR spectrum, so this magnetic resonance spectrum for the jet fuel. I actually took a little bit of jet fuel and tested it. And then I was trying to add different chemical components together to create the same chemical signature. Because the idea was, if the chemical signature looks similar, maybe the properties look similar. And then I developed these models of how the chemical signature affects different properties of the fuel. And that's kind of how we verified that this is correct until we could test it. But yeah, that was my mini chemistry project as an aerospace engineer. So in reality, when you enter, I guess, either research or engineering in general, you have studied some stuff, but you don't know everything, and probably you wouldn't use half the things you studied, but you have to learn a lot of new things that you need to be able to complete projects and get results from them.
Thank you. And I have more questions from students who had given them to me ahead of time. Before I do, are there any students here that want to ask questions? You could type in the chat, raise your hand. Okay, I'm going to go with one of the questions that I have here. How are waves used in outer space technology?
So obviously the communication bit is what we talked before, right? You still need to communicate with anything in space. But there are a bunch of other things that we do in space. So one is observing the universe. You've all studied waves. How far can we see in space? Any guesses? So the speed of light is? Isn't it 300 to 300,000 or 300 million? What is it?
I don't think they quite know off the top of their heads. Oh,
Yeah.
yeah.
Technically, I used Google. Thank you, Google. We can see 30 billion light years in space.
So where that comes from is, to see something in space, you need to wait for the light from there to come to you, right? And the speed of light is fixed. So there's like a slice of the world that you can see. And the other thing is, because this light originated at that place long time ago, you're seeing the past, not what's happening now. Which is not a bad thing, because it allows us to study the formation of the universe, because we can look into the past and basically understand how the past of the universe was different. And what where waves come into play is there's a lot of different so we don't just study visible light. We can study every form of electromagnetic wave in space. So there are different telescopes, space telescopes that are up there. Hubble is a visible light and infrared telescope, so it uses those two. There's a new one, James Webb Space Telescopes, that's going to go up. I have a few friends that were working on that. Then we have a few that are already there, and they look at the world with a different, you can think, lens. They look at, they are focused on different frequencies, different wavelengths, different types of waves. And by putting all of that information together, we can get a better picture of how things work. So there's a famous photo of, there's a famous image of the background radiation of the universe, for example, which is basically one of these space telescopes, so you can get gamma rays and further away from us, and getting an idea of kind of what the universe probably was like when it was formed. That's kind of what you get from there. So there's that sort of activity that is related to waves. And then the other thing that waves can be used for, other than all of this, is navigation. So I think 2 days ago, SpaceX had a launch. They launched Crew 1 to space station, maybe 2 days ago or 3 days ago. The vehicles that SpaceX and generally, I guess, on the western side of the space station are usually manually docked. So what that means is there's the Canadarm on the space station. The object that is gonna dock with the space station comes close. Canadarm has to go grab it. And if at some point anyone goes to the Canadian Space Agency, there's a simulator there that you can play with that actually is the simulator they use to train the astronauts. I've done that. It's very hard to do the grabbing, but you grab the object and you bring it to the docking port and you connect it, that's docking. On the Russian side, this is all automated. So on the Soyuz capsule, there are 3 antennas. And on the space station, there are 3 other antennas. And basically, these antennas send waves to each other, and they align, and then you just come and you dock. There's a similar system that Canada developed with lasers a couple of years ago, but it's not used. But that's kind of another thing. So navigating with waves and antennas it sounds not that complicated, actually, and it is not, except when they fail. So you need to still be able to manually do it, but because you don't want something to hit the space station. And the reason on the, I guess, on the western side of the space station, this is not used, is actually a case where the automated docking failed with Mir, and then like one of these capsules hit the top of the space station and broke it. So there's kind of some resistance to having everything automated. So navigation. And then finally, a thing that we do a lot in space is studying the universe, right? We're trying to understand the composition of the surface of Mars, for example. And there, a lot of the instruments that are used, it's the same instruments that we use here. So I just told you about a microscope that I use to study magnetic materials. Similar ideas there are used to study the structure of the surface of the planet or its atmosphere. So on one of the rovers, there's an instrument that basically shoots up a laser, and it uses that to measure atmospheric composition, basically based on changes on the path of the laser, for example. So things like that. Navigation, as I said, is very important. So nowadays, on the technologies that you have on autonomous vehicles on the ground, which they have tools like a LiDAR. LiDAR basically sends around light and then gets the reflection and then can understand if there's an object there or not. It's kind of like radar, which does the same thing with radio waves, or sonar does the same thing with sound waves. we use those in space too, right? For navigating on the surface of planets. So that's kind of another neat application. But all of the challenge in space is on the ground. All of these can fail. So I used to work with a robot, and it wasn't working for a day. I didn't know why. And then I learned that it has a sonar sensor that senses an object in front of it. And then on the other side of the room, we had a equipment that was running, and it was generating infrasound. So that's like waves, but they're slightly lower than sonar waves. But that infrasound was interacting with the sonar sensor, and just the thing was not working. And I spent like a day trying to find out why. So on the ground, that's fine. But if that happens in space, you don't have someone that can go there and figure out why. So you need to have backup systems for everything. So that's why on space station, we have different ways of docking. That's why on the rovers, we usually have different ways of navigating. So if one fails, you still have a backup. And that's kind of why most of these rovers are designed to be operated like for 2 years, but then suddenly they operate for 20 years. And becomes a problem too. They're like, why doesn't this rover die? There's a Russian rover called Lunokhod. It went to the moon, and it had the record for length of operation. It looks like a bathtub, and it operated for 20 years. And it became a problem for them because they really, everything was old. The system was old. It had a joystick to operate like the rover, but they had to kind of pay someone to sit there and operate this because it was still operating. Yeah, so backup systems help, I guess, increase the life of these systems.
That's great. I had never known that. And actually, we are just out of time for today. Thank you so much for being here. I know I learned a lot, so I don't doubt the students have a lot as well.
No, thanks for having me. It was fun. I hope everyone enjoyed it.
Yeah, thank you.
All right, see you next time, everybody. And thank you. We appreciate and liked hearing from you today.
Thanks. Bye.
Thank you.